my name is Sarthak Mohapatra, and this is my presentation for Lab 3, Mass of a Black Hole. The purpose of this lab was to determine the mass of the black hole using a star's position data that was provided to us in a CSV file. The result was that the model accurately depicted the motion of the star and used forces to determine the mass. In this case, I found that the mass of the black hole was 1.993 times 10 to the 31st, approximately. I used several physics principles to come to this. The first was force is equal to mass times acceleration, which I further broke down into mass times dv over dt, which is what acceleration is, the change in velocity over the change in time, which is further broken down into dp over dt, or the change in momentum over the change in time, because m times the change in velocity is equal to dp. Next, I found that dp dt parallel is equal to p hat, the direction of the momentum, times magnitude of dp dt. Then I found that dp dt is equal to dp dt parallel component plus the dp dt perpendicular component, which you can add together to find the total force, which is also, as we discussed above, equal to F net. The final equation that I used was the F sub g is equal to g 6.67 times 10 to the negative 11th times the mass 1, in this case the mass of the star, times mass 2, the unknown mass of the black hole, divided by r squared, in which r is the distance between the two. So this lab was all about breaking these equations down into code to find this. So the first thing I did was set the mass of the star, as you can see, to 1.9890 times 10 to the 30th, which was given to us, and I used delta t of 86400, or the number of seconds in a day, as was given to us. Time obviously starts at 0, and it uses a loop to count up in the time, which I'll show later. So the first thing I had to do is take this CSV, take the x and y columns of the CSV, and turn them into arrays, which I've done here. So after doing that, I took these values and found delta x and delta y by taking, for example, position 0.2 of the x array and subtracting 0.1 of the x array from it. The same thing is done for y. Then I divided that by delta t in order to find the velocity in the x direction before reiterating. Next, I set a new array called black hole mass and made it the same length as the original array and went through it. So I found the velocity initial and velocity final, and then I subtracted the two to find the delta v. I also did the same thing for momentum by taking those velocities and multiplying it by the mass of the star and setting that equal to, and then subtracting the two to find delta p. Finally, I found dp dt is equal to delta p over delta t, and F net can be equal to the same number. P hat in my case was p initial over the magnitude of p, and then I did the same thing where I found the difference in the magnitude and changed that over delta t. And I knew that from the previous equation that dp dt parallel is equal to the magnitude of dt times p hat, the direction of the momentum. Then I knew F net parallel is equal to the same thing as dp dt parallel, as is the same thing F net perpendicular is the same thing as dp dt perpendicular. The only thing I had to do is find dp dt perpendicular, which is equal to dp dt minus dp dt parallel, as was shown in the physics equations. Finally, to calculate the mass of the black hole, I took g, the gravitational constant that I mentioned above, and I found r by subtracting the x positions and y positions between the star and the asteroid and squaring those numbers, and then finally square rooting them, as I did with to the 0.5 power. Then black hole mass at each position, so this is an array of black hole masses that I took, is by taking the magnitude of the F net times r squared divided by star.mass times g. Finally, I updated the position of the star, appended the trail to make the video work correctly and to make the model look correct. Then to find the average of all of the different sums, I made another iterator and looped through all of the different masses, added them together to find a total average, the total mass of all of the different values, and then I divided that by the length of the different values to find the average mass of the black hole at each instance. So here's a video of that trial.
On a neutral court, Henry Lujan.
So what does it mean? The difference between Fnet parallel, Fnet perpendicular, and their respective dp/dt's is a case of cause and effect relationship. So while the values might be the same, the force is the push or pull that causes a change in acceleration and velocity, which eventually causes a change in momentum. And for the what if question, if you replace the black hole with another one of different mass, it would be impossible for the motion of the asteroid to stay the same. Because of the previously mentioned equation, we know g stays the same, the mass of the asteroid stays the same, the distance between the two in this case would also stay the same, and therefore in order for them to have the same force and the same positions as it has here, it would also have to have the same mass. Thank you.